This is your presenter Asloob Mudassar, and I am presenting slide number 125 of the course on laser physics. Question is, what are relaxation oscillations? How they affect the inversion and number of photons when a laser system in continuous mode is switched on? How the behavior of such a laser is dealt with when relaxation oscillations with diminishing amplitudes approach relatively stable conditions? The answer is, when a laser system is switched on, the output power shows a transient behavior where the output fluctuates with the time. This is due to the fluctuation of a population inversion and ultimately the photon numbers in the cavity. Shortly, the amplitude of these oscillations relaxes and population inversion and photon numbers converge to the corresponding threshold values, and the output power becomes relatively stable. Such oscillations are termed as relaxation oscillations, abbreviated as RO. To understand RO, we need to solve the rate equations under some assumptions. Let's choose the pump power rate as the step function. That is Rp of t is equal to 0 when the time is less than 0, that is we have not started the system, and the pump rate is also 0, and when the system has switched on, that is when the time begins to increase beyond 0, then the pump rate is a constant represented by Rp. Let us assume that the laser oscillates in a single mode. So you see that for the sake of simplicity, we are not taking the condition of the situation of multi-mode lasers, but we are considering only a single mode laser so that we can easily understand, and the mathematics will become also convenient to write. The space independent rate equations for a 4-level laser system are given by, you can consult slide number 108 for the equations shown in equation number 1 and equation number 2. That is the rate of change of a population inversion dn over dt is equal to rp minus b times phi times n minus n over tau. And similarly, the rate of change of a photon number, that is d phi over dt, is equal to va times b times n minus 1 over tau c. This whole term in parentheses multiplied by phi on the right hand side. So one will give you the rate of a population inversion and the other will give you the rate of change in photon numbers. These equations for the case of a quasi 3-level system take the following form. So for the corresponding to equation number 1 and 2, which have been written for a 4-level laser system, the corresponding equation for a quasi 3-level system have been given in slide number 111 and are reproduced as equation number 3 and 4 below. That is dn over dt is equal to rp times 1 plus f minus sigma e plus sigma a divided by v, and then the numerator is multiplied by c, then multiplied by phi and n minus f times nt plus n divided by tau, and then d phi over dt is equal to va sigma e c over capital V times capital N and minus 1 over tau c. This whole term in square bracket is multiplied by phi on the right hand side. So you can see that one set, that is equation number 1 and 2, are written for a 4-level laser system in the space independent case, and equation number 3 and 4 are written for a quasi 3-level laser system for the case of space independent case. For the details of these two set of equations, you can consult slide number 108 and you can consult slide number 111. The terms contained in these equations have been defined in question number 108 and question number 111 respectively. That is in slide number 108 And in slide number 111, the presence of the product term phi n. You see that phi n is present in all these four equations. You can see that phi n is over here, and this n multiplied by phi outside this bracket, phi n is here. And then you can see the other equations also, that is phi n is present over here, and similarly this n will multiply by the phi, and then of course we can say that phi n is present over here. So the presence of the product term, that is phi n, makes the two sets of equations non-linear. The analytic solution is thus not possible, and only the numerical solution will be discussed. For the solution of second set of equations, that is equation number 3 and equation number 4, we use the initial conditions. So we are going to list down the initial conditions for the case of a quasi 3 level system, which are given over here. That is, the population inversion at time t is equal to 0 is equal to minus nt, where nt is the total population present in the lower laser level. Because you see that in a 3 level laser system, the upper laser level, initially there are no population present in the upper laser level, and all the population will be present in the ground level, which is all in the lower laser level, which is also the ground level in a 3 level, in a quasi 3 level laser system. So in the since before the start of this phenomena, all the populations will be present in the ground state, and so that's why we have n of t, that is the population inversion at a time t is equal to 0 minus nt. Otherwise, you see that before the negative sign, we need to put the population inversion of the third level, that is the population inversion of the upper state level of the lasing system. So since that the upper state level is empty at present, so we don't have any term over here. And the second condition is that phi of t, that is the initial number of photons at time t is equal to 0, which we label as phi I. We are assuming that at least one photon is present in the cavity at that time initially. The first condition implies that at t is equal to 0, the total population was contained in the lower laser level, which is also the ground level of the system. And the second condition states that the initial number of cavity photons is 0 in the cavity. The plots of, now you see that we are going to discuss the plot of n as a function of time multiplied by VA, that is n of t times VA, and the plot of phi of t, the plot of both of these quantities versus time, are shown in figure number 1. So let me show you. This is figure number 1. The caption of the figure is plot of total inversion n times VA and the photon number phi versus t versus time for a 3 level laser system, approximately also valid for a 4 level laser system. So you see that we are plotting two quantities. The upper plot shows a quantity that is n of t times VA, and the lower plot shows the fluctuation in the number of photons, that is phi of t, that is phi as a function of time. And you know that this phi naught is actually the threshold or the steady state value of the number of photons in the cavity, and n naught times VA is also the threshold or the critical value for the population inversion in the laser system. So we have shown the plots of the change of a population inversion, which is this one, and the change of number of photons with the time for the laser cavity for a 3 level laser system, and which is also approximately valid for a 4 level laser system. And we have also shown the threshold values of these quantities. That is, we have shown the value of phi naught, and we have also shown the value of n naught times VA, where VA is the volume of the active medium, and naught is, you know, that the number of levels, number of population present in the critical state or in the steady state, and phi naught is of course the number of photons present in the steady state conditions. And of course, you see that you will notice that the time is given in microsecond. So we have started this plots for the case of microsecond, starting from 2 microsecond for a 3-level laser system, and from 0 microsecond for a 4-level laser system. But the more or less the plots for these two, that is for a quasi 3-level laser system and for a 4-level laser system, both look similarly, both look the same. Only a time difference of 2 microsecond has been shown at the bottom. So two plots have been shown in equation number 1. If we shift the origin at time t is equal to 2 microsecond, the condition that the population inversion will be zero at time initially will be 0, that is at a time is equal to 0, the population inversion is 0, becomes applicable, which satisfy the initial conditions of a population for a 4-level laser system. So you see that we are showing the two conditions together. That is, for we are showing these two plots for the quasi 3-level laser system and also for a 4-level laser system. And initially you see that when the time is 2 microsecond, the population inversion of the ground state level, the population inversion of the level number 4 will be equal to 0. The plots of figure 1 thus give the qualitative pictures of n of t, that is the population inversion as a function of time, and the photon number phi of t as a function of time, valid for a 4-level laser system, and of course also valid for a 3-level quasi 3-level laser system. The population inversion increases between the points A and B. So let me show you in the graph. The population inversion increases from the point A and B. This is the region where the population inversion is increases, and it also increases when you go beyond the point B. So up to point A to see the population inversion will increase, because you see that n of t, n as a function of time will increase upward. So it means that the population from point A to point C will increase, and of course it also increase from point A to B. But why we have split it over here up to the point B? Because this will be clear soon. The population inversion increases between points A and B under the pumping process, whereas the number of photons stays constant to their initial value phi I. So you see that when the population increases, population inversion increases from point A to B. Meanwhile, the number of photons in the cavity would stay constant, constant to its initial value. For example, if initially you are assuming that only one photon is present, then of course the number of photons will be 1 in the region from 2 microsecond to just below 6 microsecond. No number of number of photons in the cavity stays the constant up to the point just above the value of B. The population will stays the constant. That is, number of photons are not changing. When the inversion crosses the point B, and point B is the point which corresponds to the critical or the threshold value of inversion. So when the inversion crosses the point B due to the pumping process, the number of cavity photon begins to increase. So you can see that when the population inversion increases beyond the critical value or the steady state value, which is the point B, when the population further increases from B to C, you will notice that the number of photons will start increasing. You see that the peak is going upward. And this peak is slightly corresponds not exactly to the point C, but slightly above the point C in terms of time. So when the population inversion increases beyond the critical value, the number of photons starts increasing. And what happens when the value increases from B to C? The number of photons in the cavity starts increasing. It means that some process has started. So let me explain that when the inversion crosses the point B, which is the critical or the threshold value of inversion, the number of cavity photons begins to increase. Now the population inversion increases between point B and C. That is the stimulated absorption. becomes the dominant process. So you see that from the point B to C, so from B to C, stimulated absorption becomes the dominant process. The population inversion increases between points B and C. That is, the stimulated absorption becomes the dominant process. When the photon increases beyond the critical value phi naught, the stimulated emission starts dominating and the inversion starts decreasing between points C and D. So you see that this curve starts increasing at the point C, and during from point C to D, then this curve starts decreasing. So it also increases, and then you see that it starts decreasing. So when the population becomes greater than the value of phi naught, it means that what is happening? So notice over here, the population inversion increases between points B and C. That is very obvious. That is, the stimulated absorption becomes the dominant process. The photon increases beyond the critical value phi naught. So let me repeat again. So from the figure, I want to tell you very clearly that from A to B, population inversion increases. From B to C, the population inversion also increases. But B is the point which corresponds to the critical inversion. And beyond the critical inversion, that is in the region of B to C, the stimulated absorption is the dominant phenomena. Stimulated absorption is the dominant phenomena in the region from B to C. That is, the photons in the stimulated absorption, the photon maximum number of photons are being absorbed over here to increase the population inversion in the region from B to C. So after the point C, the population will start decreasing because the number of photons in the cavity starts increasing. So from point C to the middle region between C and D, that is up to this point in the region, the stimulated emission is the dominant process. And when the stimulated emission from C to onward, but well before D, up to this region, the stimulated emission is the dominant phenomena, and that's why the number of photons in the cavity starts increasing and reaches the peak value over here. So after that, when the population has fallen to a critical value, close to the critical value, what happens? The stimulated absorption now becomes the dominant process in this region. So this is the region where the stimulated absorption becomes the dominant process, and then of course the population inversion in and of course the number of photons in the cavity starts falling. And then you know that again, as I have explained, from B to C and then from to C to D, similarly the same process happen from D to E as from B to C, and you see that the number of photons stays constant in the cavity. And then when it reaches to the maximum inversion at point E, then of course what happens at that point, the number of photons begins to increase. That is, the stimulated emission process starts increasing. So when the number of photons is increasing, it means that the stimulated emission process becomes the dominant process. And when this inversion from E, the population inversion falls from point E to the downward value, and when it reaches about the critical value, then of course the stimulated absorption becomes the dominant process, and under that case the number of photons starts decreasing. So remember very simply that when the peak is, then the number of photons peak is going upward, then it means that the stimulated emission process becomes the dominant process. And under that condition, the population inversion will fall. And when the when the number of photons will starts decreasing, it means that the stimulated absorption process starts increasing, and then in that case the population of inversion should also increase, or should at least compensate, and then of course it will start to increasing. For example, it increases from point D to E, which is a purely a region where the stimulated absorption process is dominant, and similarly B to C is the region where the stimulated absorption is dominant, and then of course from C to downward the stimulated emission process is dominant, because the population inversion is falling till to the critical value, and when it reaches to the critical value, then of course the number of photons you will notice over here will start decreasing. It means that now the absorption process, that is the stimulated absorption process, has started, and it will then increase from D to E. And of course, these cycles will repeat with the diminishing values of amplitudes. You see that the B to C is amplitude is larger, then from D to E amplitude is smaller, and then of course with a decrease in amplitude, then of course you see that the amplitude variations diminishes, and then the steady state value is reached. Similarly, you can see that the number of photons increases, decreases, stays constant, then again increases, decreases, stays constant, and so on. These cycles also repeat with the diminishing amplitudes, and then of course it will converge to the constant value of or to the critical value of number of photons in the cavity. So let me say again that the population inversion increases between the points B and C. That is, the stimulated absorption becomes the dominant process when the photon increases beyond the critical value phi naught. The stimulated emission starts dominating and the inversion starts decreasing region, as in the region from C to D. So the simple case is that when the inversion starts increasing, it means that the stimulated absorption starts increasing, and when the inversion starts falling, it means that the stimulated emission becomes the dominant phenomena. When inversion decreases below the critical value, and the critical value has been labeled as NC or N naught, the stimulated absorption starts dominating the stimulated emission, and the number of photons starts decreasing. This is what I have explained, and you can reconsider the figure in order to validate this statement. In the region between D and E, the stimulated absorption completely dominates over the stimulated emission, and the number of cavity photons stays under phi naught. The cycle then repeats over and over again with the diminishing amplitudes for the population inversion, and with the background number of photons approaching the critical value phi naught with the diminishing oscillations after a fraction of a second. So you see that all this happens within a fraction of second. So after a fraction of a second, the population inversion approaches the critical steady state value NC or equal to N naught, and the number of photons approaches the steady state or the critical value N naught. And you can see that the dotted horizontal lines correspond, this line corresponds to the steady state value of the, or the critical value of the population of the number of photons phi naught in the cavity, and this horizontal or the dotted line indicates the critical population represented by N naught or NC. And of course this is the final value when the steady state operation has started. Consecutive peaks in N of t and phi of t are approximately equally spaced in time. That is, the separation between the consecutive peaks occur with the same time as the consecutive peaks in phi of t occurs. The output power shows a similar behavior to that of phi of t. The initial fluctuations in the output power are referred to as the damped relaxation oscillations, because initially when the laser will laze at some power, then of course the power will actually fluctuate in the same manner as the number of photons in the cavity fluctuates. The output power, like the N of t and phi of t, eventually approaches the steady state value. So ultimately, after some time, the steady state, since these quantities, that is the population inversion, reaches a steady state value over here, for example, similarly, the number of photon reaches a steady state value beyond this point. Similarly, the output power from the laser also reaches the steady state value beyond that point. Eventually, the output power like n of t and phi of t eventually approaches the steady state value. The behavior of n of t and phi of t in the region of small oscillating amplitudes, that is about their steady state values, can be described analytically. So we can explain the steady state values. You see that analytically. The new expressions are of the following forms. So let me again read this statement again. The behavior of n of t and phi of t in the region of small oscillating amplitudes, that is about their steady state values, can be described analytically. The new expressions are of the following forms. That is, n as a function of time is equal to n naught, which is the steady state value of a population inversion, plus delta n of t. So this delta of n of t represents small variations in population inversion about the steady state value. And we have written down this equation when we are approaching the steady state value, because we are assuming that this delta n of t, which represents a small variation in the population inversion, is small in comparison with the value of n naught. Similarly, for phi of t, that is the number of photons in the cavity as a function of time, we can write that this is equal to phi naught plus small variations in number of photons represented by delta of phi of t. So where delta of n is much less than n naught, similarly delta of phi is much less than phi naught, because we are considering the regions over here, that is the regions where we are very close to the steady state values. So over here, these variations which are represented by delta of phi and delta of n are much smaller in comparison with their critical values. So delta n is much less than n naught, and delta phi is much less than phi naught. Inserting n as a function of time and phi as a function of time, that is n of t and phi of t, in the first set of equations given as equation number 1 and equation number 2, and ignoring this term. So you see that we are ignoring this term delta n and delta phi, because the delta n is small, delta phi is small, the product is extremely small, so we can reject this product. The rate equation becomes linear in variable, that is linear in delta n and linear in delta phi. The equation, the rate equation which deals with the population inversion becomes linear in delta n, and the rate equation which deals with the which deals with the rate of a photon becomes linear in delta phi, and the analytical solution becomes possible. As n of t and phi of t satisfy the rate equations, n naught and phi naught will also satisfy the rate equations. So you see that n of t satisfies the rate equation, phi of t satisfies the rate of equation. So their depending variables, that is n naught and delta and n naught t, delta of n naught, delta of n will also satisfy these equations. That is will satisfy the rate equation for the population inversion. And since delta phi of t satisfy the rate equation of the number of photons, of the decay of photons, similarly phi naught and delta phi will also satisfy the same rate equation. So will satisfy the same rate equation. Thus, delta n of t and delta phi of t will also satisfy the equations along with their derivatives set to 0. The transformed rate equations are given by, so these are the transformed equations, that is equation number 7 and equation number 8, which we have obtained respectively from equation number 1 and equation number 2 under the substitution of equation number 5 and 6, and under the approximations that delta n is much less than n naught, and under the approximation that delta phi is much less than phi naught. So under these approximations, we have obtained these two set of equations represented by equation number 7 and equation number 8. and of course applicable for the 4-level laser system, because we have started we have obtained this equation from equation number 1 and 2, which were obtained, which were written for a 4-level laser systems. So in the writing equation number 8, that is this last equation, we have used that B times VA times n naught minus 1 over tau c is equal to 0, where tau c is the lifetime of the photons in the cavity. Taking the time derivative of equation number 8. So if you take the time derivative of this equation and introduce equation number 7, you can obtain, that is, you need to take the derivative of this equation. So you see that it becomes the double derivative of delta phi over here, and on this side it becomes the derivative of delta n over dt. So you can substitute this derivative of delta n over dt in the derivative of this equation. When you take the derivative of this both sides of this equation number 8, then you can substitute equation number 7 or in the equation number 8, and then finally you obtain this result, this equation. So this is the double derivative of d square over delta phi over dt square, and the rest of the quantities are shown. So we need to find out the solution of this equation, and we are proposing that the solution of equation 9 could be of this form, that is delta phi is equal to delta phi naught multiplied by e to the power pt. So this is the solution we are proposing for equation number 9. So equation number 10 gives you the solution, proposed solution for equation number 9. So this is the solution of equation number 9, which requires P to satisfy the equation. So when you satisfy this equation, that is, you try the solution of equation number 10 into equation number 9, you obtain this equation. That is, the condition on P is that P should satisfy this condition, that is P square plus 2 over T naught times P plus omega square is equal to 0. So this condition, that is P, must satisfy this condition in order for equation number 10 to hold as the solution of equation number 9, where 2 over T naught in equation number 11 is given by 2 over T naught is equal to B times phi naught plus 1 over tau, where omega square. So we have also an expression for omega square, which is equal to B square times VA times n naught times phi naught. And you see that if you solve P, the value of P from equation number 11 using a quadratic equation, you will find this solution, that is P is equal to minus 1 over T naught plus minus square root of 1 over T naught square minus omega square. So now you see that this omega is contained within omega is omega and 1 over T, the square of 1 over T naught square and omega square are contained within the square root. So we are now trying to simplify this by making the assumption that if omega is greater than 1 over T naught, then the P will hold like this, that is P will be equal to minus 1 over T naught plus minus iota times omega prime, where omega prime is the square root of omega square minus 1 over T naught square. The solution of equation number 10 then takes the form of a damped sinusoidal oscillation given by. So this is the solution that we have written for equation number 10 by making the substitution of a point P over there. That is the solution, that is the point P will be replaced by this one in the solution of equation number 10, and we obtain this solution. So the solution is over delta phi is equal to C times e to the power minus t over T naught into sine of omega prime in omega prime T plus phi, where C is some constant. C and phi are constants determined by the initial conditions. Now let's solving equation number 8 for delta n using delta phi from equation number 16 gives. So if you use delta phi from equation number 16 into equation number 8, which is this equation, you can find out the value of delta n also. So the solution for delta n becomes equal to this one. So if delta phi satisfy this condition, that is if delta phi has a solution like this one as shown in equation number 16, then using equation number 8 we can show that delta n, that is the change in population inversion or small changes population inversion, will satisfy this condition. So you see that this delta phi is actually the small variation in number of photons, and this delta n is the small variation in the number of inversion. That is, we are talking about this region delta phi and this region delta n. So we are now proposing, we have given a solution of delta phi for this region, and we have a solution for delta n in this region that is very close to the steady state conditions. So we have obtained delta phi and we have also obtained delta n. That is delta n from this expression. So you see that pi by 2 is present additionally in the argument of the sine functions as compared with the argument of the in the sine function contained in equation number 16. We can say that delta n leads delta phi by pi by 2. If omega is less than 1 over t naught, the two solutions given by equation number 14 are both reals. The time behavior. So where are equation number 14? So over here. So you see that if 1 over t naught square is greater than 1 over is greater than omega square, we have the real solutions. That is, p will have two values which are real. That is, the two solutions given by equation number 14 are both real. The time behavior of delta phi of t will be determined by the superposition of two exponentially decaying solutions. So you see that then delta of phi will be determined by the superposition of two exponentially decaying solutions. One decaying solution is contained in delta n, the other decaying solutions is contained in delta phi. So we have two real solutions, and then we have to add up the two real solutions will be substituted. For example, over here, then we have two solutions for delta phi, and the actual solution will then be equal to the sum of the superposition of these two solutions corresponding to two real values of point P. So the time behavior of delta phi of t will be determined by the superposition of two exponentially decaying solutions. The solution is regarded as bi-exponential. Thus we conclude that the relaxation oscillations or any perturbation during the steady state operation either decays by damped sinusoidal oscillations or by the bi-exponential law. So in one case, when omega is greater than 1 over t naught, then of course the steady state solution will be determined by the damped sinusoidal oscillations. And when we have the real values, that is when omega is less than 1 over t naught, we have two real values of p. And in that case, the steady state operation will be determined by the bi-exponential law. So you see that this is the end of slide number 125.